Hello friends, I welcome you in lecture number 31 on higher order ordinary differential equations. In lecture number 1 to 30 on higher order ODEs, we have discussed all the topics which are in our course of Mathematics 2. And now onwards we are going to discuss questions which were asked in GTU exams on the topic higher order ordinary differential equations. We will discuss all the questions one by one of the topic higher order ODEs which were asked in GTU exams. So in this lecture we are going to discuss this question on higher order ordinary differential equations which was asked in GTU Winter 2019 exam for 7 marks. Question is, using variation of parameters method, solve the differential equation d square plus 1y equal to x times sin x. And we know that this is non-homogeneous linear ordinary differential equation with constant coefficients, and we are asked to solve this with method of variation of parameters. Whatever method is specified in the question, you have to use that specified method only. If method is not specified, then you can use the method which is comfortable to you, or you can use the method which requires minimum number of steps to solve the given differential equation. But here it is already given that you have to use variation of parameters method to solve this differential equation. So you must solve this equation using variation of parameters method. We have discussed method of variation of parameters in earlier lectures on higher order ODEs. So if you have not seen those lectures, I suggest you to watch lecture number 1 to 30 first and then go from this lecture number 31. So first we write down the given ordinary differential equation. Given ordinary differential equation is d square plus 1y equal to x into sin x, and we give this number 1. Now this is non-homogeneous differential equation, and we know that to solve the non-homogeneous differential equation we have to first find out the solution of associated homogeneous differential equation. The associated homogeneous ordinary differential equation is, that is, we consider right hand side equal to 0, and we solve this equation first. D square plus 1y equal to 0, and to find out the solution of this homogeneous differential equation we have to first write down the auxiliary equation corresponding to this equation number 2. The auxiliary equation is obtained by taking d equal to lambda in this number 2. If I take d equal to lambda, I will have lambda square plus 1 equal to 0. I will consider d equal to lambda in this d square plus 1 only. If we have our differential equation in this form, f of dy equal to 0, then to write down the auxiliary equation we will replace d by lambda in f of d. Now we can easily find out value of lambda which satisfy this equation. This I can rewrite as minus 1. Minus 1 can be written as square of imaginary number I. Therefore two possible values of lambda are plus or minus I, or this I can rewrite as 0 plus or minus 1 times I. That is, I have pair of complex roots. Therefore the complementary function is the general solution of associated homogeneous equation. This is the homogeneous differential equation associated to given equation, and the general solution of this equation number 2 is called complementary function of equation number 1. And we know that if we have complex roots, we can recall that we compare this with alpha plus or minus beta I, so that we have alpha equal to 0 and beta equal to 1, and we know that if we have complex roots alpha plus or minus I beta, then our general solution is given by e raised to alpha x times cos beta x plus c2 e raised to alpha x times sin beta x. Here alpha is 0 and beta is 1, therefore complementary function is c1 e raised to 0x, beta is 1, that is cos x, plus c2 e raised to 0x sin beta x, that is sin x. E raised to 0x is 1, therefore complementary function is c1 times cos x plus c2 times sin x. Now in the method of variation of parameters, first we have to find out the complementary function, and here our differential equation is of order 2, therefore we will have two linearly independent functions in the complementary function. Here we have cos x and sin x, so we will denote one function by y1 and another function by y2. For the method of variation of parameters, we denote cos x by y1 and sin x by y2, and we find out the Wronskian of these two functions y1 and y2. The Wronskian of y1 and y2 is denoted by w, and it is the determinant with first row as y1 and y2, second row as first order derivatives of y1 and y2. y1 is cos x, derivative of cos x is minus sin x, y2 is sin x, derivative of sin x is cos x. And we know how to evaluate this determinant. We take cross multiplication, cos x into cos x, that is cos square x, minus sin x into minus sin x, that is minus sin square x, and negative negative positive, and we have cos square x plus sin square x, and we know that this is equal to 1. Therefore Wronskian determinant is 1 for y1 and y2. Now if we have second order differential equation, then we have ready-made formula in the method of variation of parameters for the particular solution or particular integral. Before that, we have to make sure that coefficient of highest order derivative is 1. Here this I can rewrite as d square y, that is y double dash plus y equal to x into sin x. And for method of variation of parameters, coefficient of highest order derivative must be 1. Here it is already 1, and after we check whether coefficient is 1 or not, we will see what is right hand side. Here right hand side function is x into sin x, that we will denote by r of x. That r of x is required in the formula of particular integral. So here we write that here r of x, that is right hand side in the given non-homogeneous equation, is x into sin x. And now we have Wronskian r of x, so we can write down the formula for particular integral of given equation, which we have given number 1 is, by the formula we know that yp is the notation for particular integral, and the formula is minus y1 times y2 into r of x divided by Wronskian plus y2 times y1 into r of x divided by Wronskian integral with respect to x. Therefore now we substitute values of y1, y2 and Wronskian. Wronskian is 1, y1 is cos x, and r is x sin x, y2 is sin x, r is x into sin x integral with respect to x, plus y2 means sin x, y1 is cos x, and r of x is x sin x, and value of w is 1. Now this is simple problem of integration. We try to evaluate all these two integrals. For that we rewrite this as x times sin square x integral with respect to x. Same thing here, plus sin x. Here I have cos x into sin x into x, and we can set this as, we know that sin 2x is nothing but 2 sin x into cos x. Therefore sin x into cos x can be written as sin 2x divided by 2, and we can take 2 outside, that is 1 by 2, and here we have x times sin 2x integral with respect to x. I am replacing product sin x into cos x by sin 2x by 2, and I take 1 by 2 outside the integral. Now to integrate this, I have to again use this formula. We know that 2 sin square x is equal to 1 minus cos 2x. Therefore sin square x can be replaced by 1 minus cos 2x by 2, and we can take 2 outside the integral. It is in the denominator, and here I write sin square x equal to 1 minus cos 2x divided by 2, that I have taken outside integral, and let me write this as it is, plus sin x divided by 2 x times sin 2x dx. Now we integrate this. We have two functions in the product, therefore we can apply the formula for integral by parts. If you recall, if we have two functions in the product, say u and v, then integration by parts is u as it is integral of v, that we will denote by v1, minus derivative of u denoted by u dash integral of v1, that we denote by v2, then positive sign derivative of u dash is u double dash integral of v2 is denoted by v3, and alternately positive and negative sign. So first function as it is integral of second function minus derivative of first function integral of second function, alternately positive negative derivative of first function integral of second function. And in this way we are going to apply this formula for these two integrals, and we keep in mind that we will consider that function as u whose derivative is 0 after some finite number of steps, so that we will have finite number of terms in this series. Now we apply this formula for integration by parts in these two integrals. Now our problem is to evaluate these two integrals using integral by parts. So let me write using integral by parts. Let me write this minus cos x by 2 as it is, and here I will consider u equal to x and v equal to 1 minus cos 2x, because derivative of x will be 0 after second derivative. First derivative of x is 1, second derivative is 0. X as it is integral of 1 minus cos 2x, that is x minus integral of cos 2x is sin 2x by 2, minus derivative of first bracket, that is 1, and integral of this second bracket, that is x square by 2, minus integral of sin 2x is minus cos 2x by 2, so that is going to be positive, and we have cos 2x divided by 4, and in the next step we will have 0 because derivative of 1 is 0. Let me check again. X as it is integral of 1 minus cos 2x is x minus sin 2x by 2, minus derivative of x is 1, and integral of this bracket, integral of x is x square by 2, integral of sin 2x is minus cos 2x by 2, so negative negative positive, and we have 4 in the denominator. Similarly we write down integral by parts. We apply integral by parts in this integral also. Again we consider u equal to x, v equal to sin 2x. X as it is integral of sin 2x is minus cos 2x by 2 minus derivative of x. Integral of cos 2x is sin 2x by 2, and there is 1 2 there, that is going to be 4, and in the next step we have 0 here. Now we have to simplify all these things. Before that, let me simplify this bracket first. This is minus cos x by 2. Here I will multiply this bracket by x, and I have x square minus x sin 2x divided by 2 minus x square by 2 minus cos 2x by 4 plus let me rewrite this again, sin x by 2 as it is. Here I have minus x cos 2x by 2 and minus minus plus sin 2x by 4, and again you can see I have x square minus x square by 2, that is going to be x square by 2. So let me write x square by 2 here, minus x into sin 2x by 2 minus cos 2x by 4, and here I multiply this bracket by sin x by 2, and I will have minus x sin x into cos 2x divided by 4 and plus sin x into sin 2x divided by 8. Now in the next step I will multiply this bracket by minus cos x by 2, that is I have x square times cos x divided by 4 minus minus plus x cos x sin 2x divided by 4 and minus minus plus cos x into cos 2x divided by 8 and plus sign cos x into cos 2x divided by 8, and these two terms as it is, minus x times sin x cos 2x divided by 4 plus sin x sin 2x divided by 8 plus sin x sin 2x divided by 8. Now we can again rewrite this as I am writing this x square first term, x square cos x by 4 as it is, and I am combining these two terms. Here I will take x by 4 common plus x by 4, and in the bracket here I have sin 2x into cos x and minus sin 2x into cos x minus, I am writing in this way, cos 2x into sin x. Similarly, let me combine these two terms. Here I will have 1 by 8 common, that is plus 1 by 8. If I take 1 by 8 common, here I have cos 2x into cos x plus sin 2x into sin x. Now this I am writing as it is, minus x square cos x by 4 plus x by 4, and you can see that this is standard formula. If you recall the formula of sin alpha minus beta, then we have sin alpha cos beta minus cos alpha sin beta, and if you take alpha equal to 2x and beta equal to x, you can see if I take alpha equal to 2x, beta equal to x, I will have sin 2x cos x minus cos 2x sin x. that is, this is nothing but sine of 2x minus x. Let me write one more step. Sine of 2x minus x is sine 2x cos x minus cos 2x sin x. So that bracket I am replacing by sine of 2x minus x. Similarly, if you recall the formula of cos alpha minus beta, then it is cos alpha cos beta plus sin alpha sin beta, and if we take alpha equal to 2x, beta equal to x, we will have this formula. So this is nothing but cosine of 2x minus x. So now we can write this simplified form. This is nothing but sin x and this is cos x, and we are having nice form for the particular solution. Minus x square cos x by 4 plus x times sin x divided by 4 plus cosine of x divided by 8. So this is the particular integral or particular solution, and finally we have to write down the general solution. So therefore the general solution is, we know that general solution is nothing but addition of complementary function and particular integral. This yp is the notation for particular integral, and let me write both the complementary function and particular integral. Complementary function is c1 times cos x plus c2 times sin x. Particular integral is minus x square cos x by 4 minus x square cos x by 4 plus x sin x by 4 plus x sin x by 4 and plus cos x by 8. And here c1 and c2 are arbitrary constants, where c1 and c2 are arbitrary constants. Because c1 and c2 are arbitrary constants, this is the general solution. So in this way you can easily answer the questions on the method of variation of parameters. If you have second order differential equation, you have to remember this formula for particular integral: yp equal to minus y1 times y2r over Wronskian integral with respect to x plus y2 times y1r over Wronskian integral with respect to x. Now this Wronskian is the Wronskian of two functions y1 and y2, which we have selected from the complementary function. If we have second order differential equation, we will have two linearly independent functions in the complementary function, and we have to find out Wronskian of those two functions using this formula. And then we have to decide what is Rx, because Rx is also used here. So for that we have to first check whether coefficient of highest order derivative is 1 or not. If it is not 1, we have to divide that coefficient. We have to divide a given equation by that coefficient, and we have to choose R of x accordingly. And once we have all these things, we substitute them in the formula, and after this step this becomes the problem of integration. So you must be good about doing integrals. So in this way we can easily answer this type of questions, and this is asked for 7 marks. So this is all about this session, and we will continue with GTU exam questions on different topics in upcoming lectures. I hope you like this lecture. Thanks for